So, sure, yeah, whenever you're ready.
欢迎大家来参加这学期的最后一次的 Math Club。那我们这次很荣幸邀请到台大数学系的戴尚年老师。那他的研究领域主要是在集值组合。那我们掌声欢迎戴尚年老师。
谢谢您，大家好。对不起，但是我说的中文不太好，所以我会用英文。So thank you very much for the opportunity to speak here. It's a great honor to be addressing you. So as you heard, I'm a professor here in the maths department. My name is Shagnik, and I work in combinatorics and discrete maths. Okay, so this is something I'd like to share with you today, and in particular, I'll be talking to you about a central problem in graph theory, namely Ramsey's theorem. Okay, so just a question, are the slides visible with the lights on? Is it clear to see? Or would it maybe be better to turn off those lights? So yeah, a little background. So when I was kind of in your shoes and I was an undergraduate, I didn't expect to be kind of going into graph theory. So in the first few years of my mathematical career, analysis was the subject I liked the most. Okay, and so I kind of was setting myself up to apply to do analysis when I continued with graduate school. But then in the last few years of my bachelor's and the master's, I took more and more kind of combinatorics courses, and I found that this was the subject that really spoke to me personally. And so 15 years later, here I am, and I hope that I may be able to inspire some of you similarly here today. I do also need to apologize. Unfortunately, there was a bit of an emergency over the weekend, so I wasn't able to kind of work on my slides as much as I wanted to. So I was hoping to have some pictures included, but I wasn't able to put those in. But we will anyway start with some stories without pictures. I guess we're grown-ups now, so we don't need pictures in our stories. But one thing I would like to say is, I don't want this to be a talk as much as a conversation. You don't need to sit here and listen to me talk for an hour or more, and I don't need to be talking continuously for that long. So if you do have any questions or something's unclear, please don't hesitate to ask. And at the same time, there's at least one point in this presentation where I'm going to ask you some questions, and I will expect you to answer them, okay? Otherwise, I will sit here and wait for as long as it takes. So let's get started. So we're going to start with a few stories just to illustrate kind of the principles behind Ramsey theory. And the first story is kind of as old as time, essentially, and this refers to the stars in the night sky. Now, of course, when we live in a city like we do here, you can look up in the night sky and see nothing, okay, or maybe just some lights. But back in the day, when you looked up in the night sky, you'd see the stars. Okay, and you see thousands of stars all over the place, okay? And kind of back in the day, we used to look for these stars for guidance. And the question is, when you have so many stars, how can you possibly get any sort of message from them? Okay, but luckily for us, we could find some messages. Okay, so there are these constellations which were very easy to spot. So for example, Ursa Minor or Ursa Major, the big bears. And then we have all the zodiac signs like Libra and Pisces and so on. And we also have some very important stars like the North Star and other constellations like Orion and Orion's Belt. And these were kind of very useful for multiple reasons. They inspired a lot of mythology back in kind of ancient civilizations to help explain how the world came to be and why we were here. But they also had more practical implications, so for example with navigation. Okay, so nowadays, of course, we all have phones with GPS, so we can look up on our maps to see where we are and where we're going. But back in the day, you didn't have these tools. Okay, so if you're sailing across the ocean and all you see is sea, it's very important to know where you are and if you're going in the right direction. And people used to look up at these stars and kind of find the familiar constellations, and then they would know roughly where they are. Okay? So it was very lucky for us that these stars, they had these constellations inside them, right? That they weren't just some random mess of light in the night sky. Okay? So that's one story. Okay? Now we'll move on to another story, which is also going back some time. This was about the Bible code. Okay? So the Bible, I'm sure, needs no introduction. It's a long holy text, okay? And in Christianity and Judaism and also in Islam, it's believed to be the Word of God. Okay, so it's a very important text, and that means that people have been studying it for ages, right? It's been around for a couple thousand years, and people have been studying it very intensely to find out the meaning, to understand the stories inside, and so on and so forth. Okay? And usually kind of these stories are allegories, right? They're stories and then there's some message behind the story that helps us learn how we should live our lives and so on. This isn't going to be a religious talk. There is some mathematics behind this, okay? Because sometimes people, when they studied the Bible, they took it much more literally than that. And so they're looking at the actual text of the Bible, and they're trying to find hidden messages in the letters as opposed to behind the meanings. Okay, and what they did is they were looking at kind of equidistant letter sequences. So to kind of write a full example would take a lot of space, but if we take kind of a short example, if you've done any programming, kind of this is a phrase which will be very familiar to you. Hello world is what the first computer program you ever write is going to say. Okay, and so what do we mean by equidistant letter sequences? What we mean is you start somewhere in the phrase, and then you look at every nth letter from so on. Okay, and you can find some, or you can try to find some kind of messages when you do that. Okay, so for example, because this is a short phrase, we aren't going to be able to find very long, very spaced out sequences. But if you start with the fourth letter and you read every letter, you find the word low. Okay, which is maybe the level of interest in this example. You can also start at the beginning and look at the first ones, and you can find a description of programming. But you could also do stuff like maybe, so in these equidistant letter sequences, you could start, say, from the third letter and look at every second letter, and you'd get something like Lu here. Okay, so you can find kind of these hidden messages. And then what they did is when they were doing this in the Bible, because they were convinced that there should be some hidden secrets in the Bible, they found that they were actually able to find a lot of interesting information with these kind of subsequences. Okay, and what kind of stuff do I mean? So for example, one thing they found is they were able to find the names and birth dates of rabbis, okay, so Jewish priests, who were born thousands of years after the Bible was ever written. Okay? And so of course, there's no way this can happen because the people who wrote the Bible, they weren't around. They had no idea when these rabbis would be born. So this was kind of, people took this as evidence that, there's some kind of secrets inside the Bible, and this can help you predict the future. Okay, and this was popularized by an American journalist called Michael Drosnin, who wrote a book called he published a book called The Bible Code. Okay, where he talked about this kind of phenomenon, and he used it as kind of a suggestion that the Bible was actually written by aliens who had come to our planet and they had kind of started human life. Okay, which frankly sounds quite ridiculous, and we're not the only ones to think that. Okay, so some mathematicians also wanted to refute these claims, and so what they did is they took another classic book, Moby Dick, which is a novel, and they did the same sort of thing. They said, okay, well, if you look at Moby Dick, then you start reading at this letter, and you read every nth letter, then you can find more hidden messages about modern events, about things like the assassination of John F. Kennedy and so on. Okay, so again, unless you believe that when Moby Dick was written, they already knew that John F. Kennedy would become president and would be assassinated at a certain time, this shows that this isn't some hidden secret message. It just happens to be there kind of somehow by chance. Okay, so that's a second story. And now we'll have one last story before we get to the point of this. And this is a more modern story. This is set in the 1950s of Hungary, which I guess isn't modern by kind of modern standards, so to speak. But compared to our previous stories, it's a lot more recent. So there's a Hungarian sociologist by the name of Szalai. Okay, and he was interested in studying friendships between children and kind of how these bonds form. So what he did is he would go and study groups of children as they played. Okay, nowadays, if you go to study groups of children when they play, you'll see them sitting around on their phones, playing some sort of games. But in the 1950s, thankfully, we didn't have iPhones or Candy Crush or Plants vs. Zombies or whatever the kids are playing these days. So kids would actually be playing with each other, interacting in person. Okay, and so what he would do is he would look at these groups of children, usually groups of around 20 children, and he would note which children played with whom. Okay, so this child played with this child today, this child did not play with that child, and so on. And he would keep track of these friendships, and he found that whenever he had groups of 20 children, no matter which 20 children they were, no matter what day, no matter how they were playing, he could always find one of two patterns. either he could find 4 children where every pair of these children were playing with each other, that they were friends, or there were 4 children, no pair of whom were friends, so they never played with each other. Okay? And so, this could maybe offer some insight into child psychology and how these social cliques form. And so he could have written a paper about this and published it in a sociology journal, but there's one thing important to note in this story, and that's that he was Hungarian. Okay? And Hungarians, they're very good at discrete maths. Okay? They learn in school what we learn in university in the rest of the world. Okay? And so he had some suspicion that maybe what he had found was nothing to do with human psychology. Okay? So he consulted with some mathematicians in the area, and being in Hungary, he had some very good mathematicians around. So he talked to Erdős and Sors and Turan, and they confirmed to him that, okay, this is a very interesting thing that you've observed, but it's got nothing to do with children. It's in fact an example of what we call Ramsey theory. Okay? And that's what we're going to be talking about today. So let's try to kind of summarize these stories and draw some moral from them. So what happened in all of these stories, we had a large system, we had a large kind of data set, and we were looking for some well-ordered subpatterns, okay, or some well-ordered subsystems. So for example, in the first story, what was our data set? It was the stars in the night sky. And what were we looking for? We were looking for these nice constellations, right? Maybe a bear here, or a hunter, or so on. Okay, in the second story, our system was the text of the Bible, okay, or any long book. And then we're looking for these messages, these sensible subsequences that spell out some words. Okay, so again, that's order. Because normally if you have a large text and I say, start from the 123rd letter and read every 45th letter, you'd expect to get nonsense. Okay, that it would make no sense. But now sometimes you can find these sensible phrases, okay, words that spell out something. And then in this third example, what was our large data set? It was a group of 20 children, okay, where we have friends and non-friends. And what were we finding? We were finding these well-ordered subsets, these subsets of 4 children, where either everyone was a friend or nobody was a friend. Okay, so there's no half and half. And so in these examples, we were always able to find these well-ordered subsystems, and it turns out that that's not a coincidence. It's not that we got very lucky. It's not that it was just random chance. It turns out that this is always bound to happen. And this is the principle, or the motto behind Ramsey theorem. It's sometimes very kind of succinctly phrased as saying, complete disorder is impossible. So if you have a large system, and we'll talk about what a system is, but if you have some sort of large system, you can try and make it as chaotic, as random, as disorderly as possible, with no pattern to how you build the system. But if it's large enough, then you're always going to find these small parts which are well ordered. Okay? And that's what Ramsey theory says. It says that it's a mathematical phenomenon, and it's something you cannot avoid. Okay? So these kind of examples, even though they might seem striking on their own, they're bound to happen. Okay? In some sense, they're like coincidences. So, these were all stories. I was kind of waving my hands a bit, but this is a maths club. Okay? So we should do some mathematics. And then the question is, how do we actually build a theory out of this? Okay, when I talk about disorder and large systems, what do I actually mean? We need to get a bit more rigorous. And in order to do so, we need to find the right language to talk about these things. Okay, the right mathematical framework. And that comes to us from graph theory and discrete maths. Okay, because if you think about kind of these stories, even though they don't quite all fit in the same mold, we see that they come from very different kind of settings. Okay, so the framework we're going to need, the type of structures we talk about, they have to be very flexible to allow for these different applications. Okay, so we need some simple framework which doesn't have too many rules. Okay, so for example, if you try to use something from algebra, like talking about groups or something, groups have a very rigid structure, right? They have these axioms that they have to satisfy, and that's very useful when you have a group, but it means that many things you won't be able to model as a group because they won't satisfy these axioms. Okay, and the same thing you can talk about like measure spaces or Banach spaces. They all have these sets of axioms which make them very useful when you try to prove something with them, but it makes it less applicable because you need to satisfy these. So instead, we're going to use something which has very little structure to it, and that's what we call a graph, okay, in graph theory. So how many of you have seen graphs before? I know some of you have. Okay, so if you haven't seen a graph, it's a very simple definition. It's just an ordered pair. You have two sets. One is a set V, which is the set of vertices. Okay, these are just the objects in the system. And then you have a set E, which is a set of pairs of vertices. Okay, so these are called the edges. Every edge is an unordered pair of two vertices. Okay, so that's all there is to the definition of a graph. Okay, and so you can see, there are no requirements about how these edges interact with each other or anything like that. It's a very, very simple definition, and that means you can model many different things with these. Okay, so for example, or to kind of rephrase what a graph is for, it encodes a symmetric relation between pairs of objects. Okay, so the vertices represent the objects, and then you put an edge between two objects if they're related in some way. Okay, relevant to how you want to use this graph. And I say it's symmetric because these edges here that I'm defining are unordered pairs. So if there's an edge from x to y, there's an edge from y to x as well, the same edge. Okay, so that's one thing. And then the other thing that's kind of convenient is that we can draw these quite simply in the plane to get a visual representation. So when we draw a graph, we represent our vertices with points, okay, or dots, and then the edges will be lines connecting them. Okay, so for example, this is what I mean by a graph. My vertices I can represent as these dots, and then if there's an edge connecting these, I just draw a line between them. Okay, and that's saying that in this binary relation, these two objects share the relation. Okay, and then I can kind of draw more and more edges if I have them in the graph. On the other hand, if I don't have an edge there, that means these two vertices are not related according to this relation. Okay, but that's kind of completely arbitrary. I don't put any requirement on kind of that every vertex should be in many edges or anything like that. Okay, that's free to me to choose. Okay, so that's what a graph is. Okay, and then graphs can be used to model many things. Okay, so for example, if you think back to our sociologist example, that's very naturally something you can model as a graph. You can take one vertex for each child, and then you can put an edge between pairs of children who play with each other, okay, or who are friends. Okay, and then inside that graph, we're looking for certain structures. Okay, and so they're kind of when we talk about Ramsey theory, there's a special class of graphs that we need to talk about, and these are the so-called complete graphs. Okay, so as we said before, the set of edges is a subset of V choose 2. It's a subset of the pairs of all vertices, or all pairs of vertices. And in the case when you have equality, that's what we call a complete graph. Okay, and that means that every pair of vertices forms an edge. So every possible relation is present. So in particular, this is not complete, right, because I have non-adjacent pairs. But if we draw every possible edge, then we'd end up with a complete graph here. Okay. So these will be kind of very important to us, as we'll see in a minute or two. And then just some notation, okay, that we'll use throughout the talk. We denote by Kn the complete graph on n vertices. Okay, so you have n vertices, and then all possible edges are present. So because you have n vertices, there are n choose 2 possible edges. Okay, and one thing to note is that when we talk about graphs, what we're interested in are the relations between the vertices. Okay, so which pairs of vertices are adjacent. What's not so important to us is what the vertices are called. Okay, so we could call, if these vertices represented children, right, we could call them by their names, right? Or we could just call them 1, 2, 3, 4, 5, and the graph we get is the same graph, right? It encodes their relations, and that's what we care about. So when we talk about these graphs, it'll be very standard to use just the integers or the natural numbers for the names of the vertices, right? So here we have the set 1, 2, 3 up to n for our n vertices. Okay? And so kind of this is our notation, and then kind of a couple observations that should be made, again, just to check that we understand everything. So Kn has n vertices, right, by definition, and n choose 2 edges. Okay, and you might ask, why do we use Kn for the complete graph? It's not because combinatorialists cannot spell. Okay, I'm not saying that they can, but I'm not saying they can't. It's because kind of when this graph theory was first invented, or first kind of written about, people were tending to use German in academic texts. Okay, so the K is from komplett in German as opposed to complete in English. And then, so the first observation is that we have n vertices and n choose 2 edges. So those are just some statistics. But then the second observation is that these complete graphs are nested. So if you have a complete graph and you look at any subset of vertices inside it, inside that subset you still see every possible edge. So that's a smaller complete graph. Okay, so for example here in this picture we have a complete graph on 5 vertices, but if we are only interested in these 3 of the 5 vertices, we look at the graph that they induce, we get these 3 vertices, maybe I'll use some colors, we get these 3 vertices, and then we get all the edges between these 3 vertices, because the original graph was complete. And so inside that K5 we find a K3. Okay? And then the point is that you don't just find one K3, you would find many, right, for every choice of the K vertices. Okay, so kind of this one copy of Kn will contain n choose k copies of Kk for every choice of vertex. Okay? So these are the complete graphs. Okay, and now how do they help us kind of define this Ramsey theory phenomenon that we talked about? Well, these will be the structures we're talking about. Okay, so when we talk about finding some order inside large structures, the structures we're looking at are going to be large complete graphs. Okay, but then what do we mean by disorder? Okay, versus order, because again, Ramsey theory says complete disorder is impossible. So no matter how disorderly a system you have, you can always find some order. So how do we represent disorder in graphs? Well, the way we do that is by coloring the edges. Okay, so we have a graph, and when we have a complete graph, it's all determined, right? We have n vertices, we have all n choose 2 edges, so there's nothing to determine. So we introduce some kind of randomness or some chaos by coloring the edges. Okay, and so in this, as a first step, we'll color the edges with 2 colors, which traditionally we call red and blue. Okay, and these can model different types of relationships between the vertices. So again, if we go back to our kind of example with the 20 children, right? I said before that you can construct one graph where the vertices are the children, and you put an edge between 2 children who play. Okay, but another way to model the same thing is to have a complete graph on 20 vertices. So you have all children, but you have all possible pairs as edges, but then you color the edges red if they're friends, and blue if they're not friends. Okay, so you have these 2 types of relations, and you can model them using this coloring. And now this can introduce some disorder, right? Because you don't know in advance who's going to be friends, who's not going to be friends. So now you have many different possibilities. Okay, and then what do we mean by finding order inside here? Well, order for us will mean subsets of edges, subsets of vertices where all the edges inside are the same color. Okay, so you're coloring the whole graph with these 2 color edges, but now you want to find small parts of the graph where you only see one of the colors. So everything is very neat and orderly and uniform, as opposed to the chaotic 2-colored complete graph. Okay? And so, as I said before, we can really recast the third story in this very language. So the vertices are the children, your edges you color according to friends and not friends. And then what did Salai find? He found that whenever he had 20 children, he could find these 4 children who are either all friends or all not friends. So what does that mean in our graph? It means we find 4 vertices in our graph where all 6 edges between those 4 vertices are either all red or all blue. Right? So you only see one of the 2 colors on these vertices. And so then the kind of question is, can you always find this order? Okay? So if I have a complete graph, if I 2-color it, can I always find some subgraph where all the edges are the same color? Okay? And as I've already spoiled, the motto of Ramsey theory is that complete disorder is impossible, which means it should always be possible to find such order. And indeed, that is the content of Ramsey's theorem. So a little bit of history, and again here I would have liked to put a picture of Ramsey, but I didn't have time. I'm not going to try to draw a picture of Ramsey on the board, because that would be very rude to him. Okay, so Ramsey lived a bit over a century ago, so he was born in 1903 in England. Okay, and then he went to Cambridge University, to Trinity College, and he graduated in 1923. Okay, so not too bad. And then he made kind of in his academic life after that, he made major contributions to kind of 3 different fields: to mathematics, and specifically to logic, to philosophy, and to economics. Okay, so in all of these fields, he has results and theorems named after him. Okay, so he was a man of many talents, and then unfortunately he died quite young. Okay, he died at the age of 26 in 1930. Okay, possibly, according to Wikipedia, from some infection from swimming in the rivers. Okay, so don't do exercise; it can kill you. But we remember him today, in this talk at least, and in combinatorics, for his theorem, which we call Ramsey theorem, which gives its name to this field. So this he proved this was published in 1930, and it says exactly what we're talking about. In any red-blue coloring, you can always find these subsets where everything is the same color. Okay, but one thing to note, in contrast to what we've been talking about, this is in an infinite setting here. Okay, so I've been talking about finite graphs because that's all I can draw without running out of chalk. But you can also talk about infinite graphs, right? In the definition of graphs, I never said anything had to be finite. And so here, your vertices are the natural numbers n. Okay, so 1, 2, 3, and so on. Forever, you have infinitely many vertices. And if you have infinitely many vertices, you have infinitely many pairs. And now Ramsey says that if you take all of these infinitely many pairs and you color each pair either red or blue, right? Now there's completely unbounded scope for chaos, right? Because every vertex is in infinitely many edges. You can color them any way you want. Lots and lots of choices. Okay, so there are uncountably many colorings that we're talking about here. But Ramsey says that in each one of those colorings, you can always find an infinite subset where all the edges are the same color. Okay. Now, of course, it's not difficult to find infinitely many edges which are the same color, right? Because you only have two colors, you have infinitely many edges. At least one of the color classes must be infinite. But this is saying you can find an infinite set of vertices where all the edges between those vertices are the same color. Again, this is much harder to do. And if you think about it, when you first think about it, you might not believe that this is possible. Right? It should be very easy in every infinite subset to make sure that there's one red edge and one blue edge. Okay? But it turns out that that's impossible. Okay? And so this is kind of the fundamental theorem of Ramsey theory. Right? This is what kind of gave birth to everything. There are a couple extensions. Okay? So we won't talk about the proof of this in particular. Later we'll show a proof which kind of implies this result if you carry it if you push it a little further. But what I would like to talk about is a couple extensions at this point. So a couple of ways you can make this stronger, just to show how versatile this theorem is. Okay? So one extension, the first extension, is having more colors. Okay? So far we've talked about coloring everything red or blue, but why limit yourself to these two colors? Okay? So of course, okay, maybe two colors because back in 1930 things were in black and white. But we now have color TV, right, which can show quite a lot of colors, in fact. And so what happens when you have more colors? Is it still true? And it turns out that it is. Okay? So if you have, again, a coloring of the infinite complete graph with any number of colors, any finite number of colors. Okay? So R here is any natural number. You fix the number of colors. You color the complete infinite graph with those R colors. Then again, you can always find an infinite subset where every edge is the same color. Okay? And of course, this gets harder when you have more colors, right? Because there are many more options, but it turns out to still be true. Okay? And it's not too hard to prove when you know the two colors theorem. So let's look at the proof. The idea is that you go colorblind. Okay? So you merge some of the colors, and then you can imply recursion. So let's think about the first case. So if you have three colors, so let's say that they're red, blue, and green. Okay? You can imagine that you go blue-green colorblind. So you can't tell the difference between blue and green anymore. So now instead of seeing a three coloring, what you see is a two coloring, right? Because the only colors you can see are red and then this blue-green color, which looks the same to you. But now if we only have two colors, we can use Ramsey's original theorem. Okay, and so what does Ramsey's theorem say? It says that we find an infinite clique, an infinite complete graph, where every edge is the same color. So there are two options. Either every edge is red, and then we're done, right? Because the original edges are red, and so you found your infinite clique where all the edges are the same color. So in that case, you're done. The other case is that the infinite clique is this blue-green color, which wasn't actually a color. But now we can take this infinite blue-green clique, and in our original coloring, that means every edge inside this infinite clique is either blue or green. Okay? But again, that means we have a two-coloring of the infinite clique. Now this clique, it's maybe defined in some infinite set S instead of the natural numbers 1 up to infinity. Okay? But again, the names of the vertices don't matter. Right? And our infinite clique is countably infinite, so you can imagine we can call the vertices 1, 2, 3, and so on. And then we can again apply Ramsey's theorem. We have a two-coloring of an infinite complete graph, so we find an infinite clique inside it, where all the edges are either blue or green, and in either case we're done. Okay? So if you know the result for 2 colors, you know it for 3 colors, and then of course you can repeat this process. Right? You can always merge the last pair of colors, apply the previous result, and then apply the 2-color version again if you have to. Okay? So it's true if it's true for 2 colors, it's true for any number of colors. Then another thing I wanted to mention, just because it's useful for applications, is this hypergraph version. Okay, so I won't define what a hypergraph is formally, but as I said, when we talk about graphs, our relations involve pairs of vertices. Right? So we put an edge between 2 vertices, but you might have more complicated relationships, right, which involve more than 2 vertices. Okay, and so for any number k, you can define a k-uniform hypergraph where you look at subsets of k vertices instead of just 2. Okay? And then Ramsey's theorem says that for any fixed k, if you again red or blue color the k subsets now, okay, instead of just the pairs, then you can again find an infinite subset where all the k sets will get the same color. Okay? So we won't talk about the proof of this, but it's not as easy to prove as the multicolor version, but it's also not the most difficult thing in the world to prove. Okay? So one thing to note is that the k equals 1 case, this is just a pigeonhole principle. Because this just means you're coloring the vertices, right? And you're coloring infinitely many vertices with 2 colors. So again, one of the classes must be infinite. Okay? So this is kind of trivial. The case k equals 2 is the Ramsey theory we've seen before. And then for larger k, you're dealing with more and more complicated subsets, right? So if you think about the children, it depends on what game they're playing, right? So if they're playing chess, for example, that's a 2-player game, so you could represent that with edges. If they're playing something which involves more than 2 players, like if they're playing football, then that maybe involves, okay, it doesn't work with 20 people, but suppose you had 200 kids and they're playing football, then they maybe play 22 people, right? 2 teams of 11, and then your sets are sets of 22 children. Okay? So then the point is that for larger k, you can prove it by induction on k. Okay? And kind of this induction works, but then it kind of gets kind of more and more complicated. Okay? So we've seen a couple of extensions before we go here. So you can have multiple colors, you can have larger sets. You can, of course, combine these extensions. Right? If you know the k set version for 2 colors, then in exactly the same colorblind argument, you know it then for any number of colors. Okay? But there are some limits to how far you can go. Okay? It's not true that everything you want in the world is true. Okay? So there are some extensions that don't really work. So one problem is if you color with infinitely many colors. Okay? So in the previous slide, we said for any number r of colors, Ramsey's theorem works for r colors, but it doesn't work if you have infinitely many colors, right? Because obviously you can color each edge a different color. And then you'll never find even a finite set where all the edges are the same color. I should mention there is a version of Ramsey's theorem which works when you have infinitely many colors. Okay, but then you cannot try to find things where everything is the same color. What you can find is either things where everything is the same color. Maybe it's an interesting fact. So show you the different possible colorings. Okay, so what you want in Ramsey theory is that everything is the same color. Right, and so on. So for example here, all the edges are red. Okay. Now if you have many colors, then you can avoid these kind of things by coloring every edge a different color, right? So you could color this edge red, I could color this edge blue, this edge white. I can go a little bit further. I can color this edge green, this edge yellow, and this edge orange, and now I've run out of colors, but so on. Okay? So if I do this for my entire coloring, then I'm never going to find a structure like that. Okay? But there's also other things you can do, which are a little weird. What I can do is I can color every edge according to its first vertex. So edges from the first vertex, I can color green. Then edges from the second vertex, I can color blue. Edges from the third vertex, I can color red, and so on. Okay. Now again, I'm never going to find something where everything is the same color, right? But I'm also never going to find something where everything is a different color, right? Because whenever I have a first vertex, the edges to all the later vertices will all be the same color. And then I can take the same coloring, but I can kind of reverse it, where I color the edges according to the second vertex. Right? So every edge that ends at the second vertex, I color green, but there's only one such edge. Every edge ending at the third vertex, I color blue. Every edge ending at the fourth vertex, I color red, and so on. Okay? And this kind of is conceptually similar to this, but in practice it's different, right? Because here, every color is used infinitely many times. Here, every color is only used finitely many times. Okay, but again, here I'll never find a monochromatic structure. I'll never find a rainbow structure. I'll never find something like this, because each color is used finitely many times. Okay, and so on. But then there's a version of Ramsey's theorem called the canonical Ramsey theorem, which says that if you take the infinite complete graph and you color the edges any way you want, so any number of colors, okay, you can use finitely many colors, you can use infinitely many colors, then you'll find an infinite subset which has one of these four types of colorings. Okay? So yeah, when you first see it, I was happy to see your reaction. It's very surprising, right? Because here you've got complete freedom in what you want to do, but there's one of four things which are unavoidable. And in particular, these three colorings use infinitely many colors. Right? So if you only have finitely many colorings, you have to find an infinite monochromatic subset. Right? So this proves the kind of finite many colors case, and you can prove this using the finitely many colors case. Okay? So those things are kind of equivalent. But yeah, so that's just an aside to show you that kind of you can say more things, but if you want to find infinite monochromatic subgraphs, you cannot allow having infinitely many colors. Now the other thing we've talked about in this slide here is we looked at larger subsets. Instead of just looking at pairs, we said, well, if you look at all triples, you can make them the same color. If you look at all four sets, you can make them the same color, and so on. So you might ask, well, can I make it so that all subsets are the same color? Okay, so I have a coloring now, not of pairs, not of just triples. I color all the subsets of the natural numbers, red or blue. Can I find an infinite set where all the subsets have the same color? Okay, and again, this is a non-extension because the answer is no. Right? You can't, that's asking for too much. And again, it's quite simple to see why. You can color all the sets of size 1 red, all the sets of size 2 blue, and then you're done. Right? Because any infinite set will contain sets of size 1 and will contain sets of size 2, and so it will have red and blue subsets. Okay, so this is asking for too much. It is important that all the sets we look at are the same size. Okay? But again, there are some kind of, there are some results which look at things like this, where you're looking at all subsets and what kind of structures can you find there. Okay, so that's kind of some original, that's the original theorem of Ramsey, and kind of these extensions I'm talking about, they didn't come later, they kind of are originally from Ramsey himself. Okay, so these are kind of straightforward examples. And so one thing I want to say is that there are many applications. Okay, so we mentioned some stories at the beginning. Those are more kind of motivation to introduce this kind of topic. But Ramsey's theorem itself, the mathematical statement, has many applications in mathematics and in science. Far too many to count, but I'll mention a few here that might be of interest. So one important application which has been studied a lot is in geometry. Okay, if you have some points in the plane, right? Again, the points can be kind of arbitrarily positioned, kind of like stars in the night sky. But then in geometry, you have this very nice notion of convexity, right? And the convex hull of a set, points in convex position have very nice properties. They're much nicer than points in arbitrary position. Okay? And so then the question is, if I have many points in the plane, can I always find points in convex position? Okay? So if I have, for example, so I'm kind of putting points here. Right? These points are not in convex position, and the kind of convex hull is rather disappointingly only a triangle. Okay? But the point is that I can find some subsets here which are maybe more nicely positioned. So for example here, if I look at this subset, that's a larger set that is in convex position. Okay, and so this will have nicer properties than if I just look at the convex hull itself. Okay? And so then the question is, if I have points in the plane, if I have many, many points in the plane, can I always find many points in convex position? And the answer is yes, because of Ramsey. Well, not because of Ramsey, but using Ramsey's theorem, you can show that the answer is yes. Okay? And kind of there are a few different ways to prove it, but kind of you can prove it using the hypergraph Ramsey version. Okay, so one way to think about it is you color 4 sets of points. Okay, so I look at any 4 points and I color them red if they're in convex position. Okay, so for example, these 4 points are in convex position, so I'll color them red, but then you color the points blue if they're in convex position. In concave position, sorry. So these 4 points are in concave position, right? This is not convex, and so I color them blue instead. And then you can show, so what does Ramsey's theorem say? It says if I have a large enough set of points, then I can find a large set of points where all the 4 sets will be the same color. And then you can show that it's impossible to have a large set of points where every 4 set is in concave position. Okay, and so it has to be in convex position. And then you can show that if every 4 set is in convex position, then the entire set is in convex position. So that's one application. Then you have kind of applications in number theory. Okay, and in fact, some of these applications from number theory are older than Ramsey's theorem itself. Okay, so this kind of problem has been studied in combinatorial number theory for a long time. And so kind of one typical application is if you look at the natural numbers and you color them with finitely many colors, can you always find a monochromatic sum, x plus y equals z? Or can you always find a monochromatic arithmetic progression? Right, so n plus d, n plus 2d, n plus 3d, and so on. And again, these are Ramsey type theorems, and the answer is that yes, you do always find these structures. Okay? And then going a bit further afield, if we move to theoretical computer science, then there are many questions in complexity where Ramsey theorem plays a key role as well. Okay? And so kind of one example that I found when searching this online, if you want to sort the integers, how long does it take? Okay? And if you're taking this semester's Combinatorics 2 course, we've talked about the complexity of sorting, and we know that to sort n integers, it takes n log n time. Okay, and that's best possible. But now, that's if you only have a single processor. Okay, nowadays we have huge supercomputers which can process things in parallel. And so then you can ask, okay, if I can process in parallel, how long does it take to sort n integers? Okay, and then it's always difficult to find lower bounds because you need to prove that any algorithm will take a long time, and having Ramsey theory makes it is very helpful for proving these lower bounds. Because the data you're dealing with can be very arbitrary, can be chaotic, but using Ramsey theory you can find subsets of that data where everything looks nice. And then it's easier to analyze how your algorithm will work on this data. Okay? And so it's used in computer science as well. But there are really many, many examples, okay, and applications. And you can find many papers where people talk about applications of Ramsey theory. So they say, Ramsey theory is interesting. Here's a list of kind of 10 interesting applications from recent papers and things like that. Okay, but there's a slight problem, okay? And the problem is that when we talked about Ramsey's theorem was talking about infinite sets, infinite graphs. And if I want to talk about an application and a real-world application, I don't have an infinite graph. Right? Like when I had a sociologist, he had 20 children. He didn't have infinitely many children to look at, right? Which is a good thing in many ways, but it's a problem if you want to use Ramsey's theorem. Okay? So that's bad, but then there's some good news, and the good news is that because we don't have infinite graphs, we also don't need to find infinite subgraphs. Right? Because Ramsey's theorem it required infinite graphs as the input, but the output it gave us were infinite graphs as well. So it was a very strong theorem. It's much stronger than what we need for applications. Okay? So for an actual application, what we want is a finite version of Ramsey's theorem. Right? So for a sociologist, for example, he was looking for sets of 4 children where everything was well ordered. Okay? If we're kind of sorting numbers in computer science, then maybe we have n numbers, and we want to find some subset of a given size where everything is nice and orderly. And so it turns out that, again, from Ramsey's theorem, which was this infinite statement, you can deduce a finite statement as well. Okay? And so what does a finite statement say? It says, well, you give some n, and the little n here will be the size of the ordered subset you want. So it's the size of the subgraph where everything will be the same color. And then Ramsey says that for every choice of little n, there's going to be some big N, such that if you have a complete graph on this big N many vertices, and then you color the edges red or blue, any way you want, I can always find little n vertices inside there where everything is the same color. Okay? So you tell me how big the order you want is, and then I'll tell you how big the disorder has to be so that you can always find the order inside it. Okay? So for example, if you wanted the 4 children, all friends or all non-friends, so ordered set of size 4, then Saleh's observation was that, well, if you have a big set, so your capital N is 20, then that seems to be enough. Okay? So this is the finite version, okay? And then kind of, sorry. No. 1 second. Okay, it just seems to be skipping to the end. And I don't seem to be able to close it. So I did promise you some chaos. Here we go.
I'm not sure what happened.
Yeah, me neither. Do we maybe need to restart the laptop?
I guess so.
Okay, I'll make some space for some new pictures. Sure, no problem.
Hope it's fine.
Should be, thanks. Seems to be. So let's go back to where we were. Yeah, okay.
Okay, cool.
Okay, thank you. Apologies for that break. So this is where we were. We said that you have the finite version, which promises that if you only want to find a finite set where everything is ordered, it's enough to have a larger but finite graph to begin with. Okay? And then, so if you have a large enough complete graph, you can find a large ordered set, okay, rather than infinite in both cases. And then one thing to note is that, as I said, this can be deduced from the infinite version. Okay, so again, this goes back to the original work of Ramsey. The infinite version implies the finite version. Okay, okay. So then this brings in a natural question. So we said if you want to find a large ordered set, you should start with a coloring of a large enough big graph. Then how large does large enough have to be? Okay. And Ramsey's proof is existential. Okay, so he was proving this in logic. So it just proves the existence of this capital N. It doesn't say anything about how big capital N actually is. Okay, and again, if you're dealing with an application, that is then less helpful. Okay, so for example, if you're a sociologist and your rival Salai published a paper about finding 4 kids who always play together, and you say, I want to do better than Salai. I want to find groups where 5 kids always play together. Ramsey's theorem tells you, yeah, if you have n children for a large value of n, it's enough to find them, right? But it doesn't tell you what n is. So you don't know if you should take, 30 children, should you take 100 children, should you take 1,000,000 children? Ramsey's theorem doesn't tell you that, okay, the original version. So then we can define this extremal parameter, okay? And as combinatorialists, this is what people were quick to do. So this is what we call the Ramsey number. So Rn is the smallest big N, such that if you take the complete graph on big N vertices, you color the edges red or blue, you're guaranteed to find either a red copy of k little n or a blue copy of k little n. Okay? So this is the smallest value of large enough that works for Ramsey's theorem. Okay? It tells you how big, how much disorder do you need before you find the order of the size you want. Okay? So this was slightly unfortunate timing because we just had a break, but this is where I wanted to give you a quiz to unlock the rest of the talk. Okay, so let's understand the definition and figure out what these values are. Okay, so can someone tell me what R of 1 is? It's just 1, right? Because if I only have one vertex, then I have 0 edges, so I'm not actually coloring anything. And what is my goal is to find a single vertex. Well, that's what I start with, right? So R1 is 1. Very good. And that wasn't very difficult. Okay. What about R2? 2? Yeah. Because now I have 2 vertices. Now I do have an edge, so I can color it. I can color it red or blue. But my goal is to find an edge, a graph where the edge is the same color as itself, right? There's nothing else to compare it to. So no matter if I color it red or blue, I find a monochromatic copy of K2. What about R3? Okay, so finally we have some disagreement. That's good. So let's note that it cannot be 4. Right? Because if I have 4, what can I do? I can split my 4 vertices into 2 parts. Okay? I can color the edges inside each part blue, and I can color the edges between the parts red. Okay? And this will not have, what am I looking for? I'm looking for a triangle where all the edges are the same color. That won't exist here, right? Because how could I have a red triangle? It's impossible, right? Because no matter where my 3 vertices are, 2 of them will be on the same side and their edge will be blue. But I also can't have a blue triangle because each side only has 2 vertices. Okay? But I cannot do this with 5 vertices, right? Because if I split the 5 vertices into 2 parts, one side will have 3, and therefore will give me a blue triangle. Okay? However, if you play around with it a bit, it turns out that you can find a coloring of K5 without a red or a blue triangle. Again, the way to do it is to draw 5 cycles instead. Okay? So here we have a coloring of K5, and if you check any 3 vertices, 2 of them will be next to each other on the outer cycle, so you'll get a blue edge, but 2 of them will also not be, so you'll get a red edge. Okay? And then you can think, okay, so that shows me that it's not 5, is it 6? And then it turns out that indeed the answer is 6. Okay? And let's understand why. This is another nice proof you can find if you give yourself enough time. Suppose I have K6. Okay, so I have 6 vertices. Now look at one vertex that has edges to the 5 other vertices. These edges are colored red or blue, so 3 of them have to get the same color. Right? So without loss of generality, let's say there are 3 blue edges. Now consider the edges between these 3 blue neighbors. If I have a single blue edge there, I create a blue triangle, and I'm done. Okay? But if I don't have any blue edges, then these 3 vertices form a red triangle, and so I'm done. Okay, so when you have 6 vertices, it's unavoidable to get a red or blue triangle. If you only have 5 vertices, you can avoid it. Okay, so that shows you that R3 is 6. Very good. No prizes for guessing what the next question is. What is R4? Now, yeah, does anyone see immediately what the answer is? Good, you shouldn't, okay? I'd normally give you a bit more time to think about this, okay? But we want the talk to end today. So it turns out the answer is 18, okay? You can prove, using similar arguments like this one, that if you have 18 vertices, you can always find 4 vertices where the edges are all the same color. What's a bit harder is to show that 17 vertices isn't enough, but it turns out that there's a coloring, which in fact is the so-called Paley graph. It comes from number theory. So if you have 17 vertices, you view them as the elements of the finite field, F17, okay? And then you color them based on whether the difference is a quadratic residue or not. Okay, so you take the edge xy, and you color it red if x minus y is a square, and blue if it's not a square, and then you show that this graph doesn't have 4 vertices where all the edges are the same color. Okay? Why would you come up with such a construction? No idea, but it works. Okay? And that's what's important. In particular, Salai's story, Salai was looking at groups of about 20 children. 20 is bigger than 18, and that means that he was always able to find these 4 kids. Okay, R5. This is the last question in the quiz. And again, I don't expect you to know what the answer is. The reason I don't expect you to know what the answer is because I don't know what the answer is, because nobody knows what the answer is. Okay, so all we know about R5 is that it's between 43 and 48. Okay, and in fact, this is a relatively recent result. I think this was 2017 or maybe 2019. Okay, before that, the bound was 49. That was known earlier. Okay, so for R5 already, we don't know what the answer is exactly. And this might surprise you a little bit, okay, because 5 is not a big number. So how come we don't know what the answer is? So we have time for another story, okay? And this is not my story. This is a story of Erdős, which is a name we're going to hear a fair bit in the rest of this talk. So Erdős said, imagine that we're sitting around living our lives, and then some aliens come and invade the Earth, okay? And they say, tell us what R5 is, or we're going to destroy your planet, okay? But they're nice aliens. They know we don't know the answer, so they say, okay, we'll come back in a year, right? And either you give us R5 or we blow up your planet. And then Erdős said that if this were to happen, okay, then what we should do is we should gather all our mathematicians, we should gather all the strongest computers we have, and we should try and find out what R5 is. Okay, figure out which of these 6 numbers is the correct answer. And then hopefully within a year we can find the answer and we can give it to the aliens and we can survive. Okay? But suppose we find the answer and we give it to the aliens, but they're not nice aliens. Okay? So they say, okay, thank you for R5. Now tell us what R6 is, or we'll come back and we'll destroy your planet in a year. Okay? And Erdős says that when this happens, then instead of calling our mathematicians, we need to call the military, and we need to figure out how to destroy these aliens when they come back. Okay? Because finding out R6 is going to be impossible. Okay? And so you might ask, well, okay, why is it so impossible, right? 5, 6, these are small numbers. Even 43, 48, those aren't very big numbers. Okay? So why can't we just take a supercomputer and test the color rings? Okay? But you need to understand how quickly these things grow. So suppose you want to check if R5 is equal to 43. What does that mean? You want to check, we know that's the smallest it can be, right? So we know on 42 vertices there is a color ring which doesn't have 5 vertices all red or all blue. Okay? We want to check whether such a coloring exists for 43, the complete graph in 43 vertices. But now the complete graph in 43 vertices has 43 choose too many edges, which is 903. But now each edge can be colored red or blue. So the number of colorings is 2 to the power 903. Okay? So all of a sudden this is a very big number. Now, it's not immediately apparent maybe quite how big this number is, right? Because I can write it here on the slide and it doesn't take up very much space. Okay? So I did some calculations. This is one of the reasons I don't have pictures in this talk, because I spent all my time on this. But if you took every atom in the universe, and if you told every atom to check a coloring, and if it took every atom 1 millisecond to check a coloring, and checking a coloring is non-trivial, right? Because you have these 43 vertices, you need to check every set of 5 vertices to see if the edges are all the same color or not. Okay? But suppose these atoms are very quick and they can do this in a millisecond, it would take 10 to the 179 years. Okay? And the age of the universe is less than 10 to the 10. Okay? So this is why Erdős is saying that, Erdős was still hopeful that R5 was maybe solvable, but you can see kind of how quickly these problems become intractable computationally. Okay. So yeah, we can't brute force it. We have to be a bit clever about these things. Okay? But even if we're clever, we kind of have to give up on finding these numbers exactly. Okay? For small values we could do it, but these are just growing too quickly. There's no discernible pattern there. So instead of trying to figure out exactly what Rn is, we have to satisfy ourselves with getting some bounds, but knowing roughly how big is it. Okay? Because 43 to 48, there's a bit of a gap, but these two numbers are pretty close to each other. Right? So we know roughly how big it is. So we need to understand what it means to prove bounds for the Ramsey number. Okay? And so to prove that the Ramsey number is at most some number capital N, that means we need to prove that in every red or blue coloring on Kn, you can either find a red copy of K little n or a blue copy of K little n. Right? That's what it means to prove an upper bound. And what is the problem? Why is this difficult? It's difficult because there's so many different colorings. Okay, and your proof needs to work for all of the colorings. Okay, so that's what makes upper bounds challenging. Now, why are lower bounds challenging? Well, let's first understand what a lower bound means. To prove that R of little n is bigger than big N, you need to give a single coloring of K big N, which doesn't have any red or blue copies of K little n. Right? You just need to give one coloring. Like in this case, you gave this one coloring of K5. Okay. So, finding one coloring doesn't sound so hard. Okay, so what is the problem? Well, the problem is kind of numerically, what do I have control of? I have control of the colors of the edges. And how many edges are there? There are n choose too many edges. Okay, but what do I need to, where are my constraints? My constraints are on every copy of Kn, K little n. I need to make sure it's not all red and not all blue. Okay, but as we said earlier, the number of copies of K little n will be capital N choose little n. Okay, and this will grow much quicker than n choose 2. Okay, so my problem is going to be oversolved, and that's why I do not expect to find a solution. Right? And the problem is I need to keep track of very many constraints, but I have very few degrees of freedom. Okay? So those are kind of the challenges. Now I'd like to kind of, we're getting towards the end of this talk, I'll give a few bounds, And I'll maybe take the liberty of showing you a little bit of the proofs. Okay, so the first proof, or for the first bound, is the simple bound of Erdős and Székely, which says that the Ramsey number is at most exponential. Okay, so again, Ramsey's original theorem only proves that this number is finite without giving any bound, any effective bound. So Erdős and Székely, they studied this a little bit after Ramsey's original theorem came out, and they gave an exponential bound. Again, this is rather simple. So what is the idea? It's a generalization of this argument here. Okay, so suppose I have capital N vertices. Okay, now choose one vertex. Now this has edges to all the other vertices. Those edges are all colored red or blue. So by pigeonhole, for half of the other vertices, all the edges will be the same color. Right? So I can find some set of half of the vertices where all of these edges are the same color. Okay? But now I repeat the picture in this top half. Okay, so I only look at the top half. I take another vertex. All the edges here are the same color, red or blue. So I can find another set of half the vertices where all the edges will be the same color. Maybe this time they're all red. Okay? But remember, from the first vertex, these edges are all still blue. Okay? Now this is not going to give me a monochromatic clique, right? Because I'm getting different colors. But still, I'll repeat the process. Okay? So I take my next vertex. I find half of the vertices where all the edges are the same color. Maybe they'll all be blue. Okay, and I repeat this process. And so what do I end up with? I end up with the sequence of vertices. Okay? And I also, for each vertex, I have a color. So the first vertex was blue, the second vertex was red, the third vertex was blue, and that color determines the color of the edges going later. Right? So these edges are all blue. These edges are all red. These edges are all blue, and so on. Now, how long is the sequence going to be? Well, every time I go from n to n over 2 to n over 4 to n over 8, right, I'm losing a factor of 2 each time. So if n is equal to 4 to the n, which is 2 to the 2n, then I can get a sequence here of length 2 times little n. Okay? Now in this sequence, each vertex comes with a color. So if I have 2n vertices, then I can find a subsequence of little n vertices where the colors are all the same as well. And then on that sequence, all my edges are the same color. Okay, so we get a monochromatic sequence of length n. Okay, and that gives me my clique. And so this shows us an exponential bound. Of course, exponential numbers are very big, okay? But it at least gives us a finite bound that you can put your hands on and actually calculate. Right? And like if you compare it to kind of these values, 4 to the n is quite a lot bigger than these, right? Like 4 to the 5 is 1024, right? Whereas we know that this is smaller than 50. So it's maybe a gross overestimate, but it's a bound at least. Now you can be a bit more careful. Okay, and you can prove this bound in terms of this binomial coefficient. Okay, but then you don't really save much. So if you analyze what this binomial coefficient grows like, it's still 4 to the n divided by square root n. Okay, and square root n is insignificant compared to 4 to the n. Okay, so that's a upper bound. Okay, now what about lower bounds? So there's an observation of Turan that these numbers have to grow reasonably quickly, that they grow at least quadratically. Okay, and this quadratic bound is a generalization of this coloring here. So to show that r of n is bigger than n minus 1 squared, what did Turan say to do? He said, take your vertices and split them into groups of size n minus 1. Right? So n minus 1 groups of size n minus 1 each. Oops. Okay? And then Turan said, inside the group, color all the edges blue, and then color all the edges between two groups red. Okay? And then again, this doesn't have a copy of Kn where it's all the same color, because if I have n vertices, I have to have vertices from two different groups, and that edge will be red. But because I only have n minus 1 groups, I also have to have two vertices from the same group, and that edge will be blue. Okay, so this is a good coloring, and that gives me the lower bound. Now, Turan believed that this was the best possible bound. Okay, and he had some good reason to believe this. Why did he believe this? Well, he said intuitively, if I don't want there to be a blue copy of Kn, it would help to not have very many blue edges. Right? Because if I don't have many edges, then it's harder to construct a clique. So I want to have as few blue edges as possible. But now, if I don't have many blue edges, I will have many red edges. So then the question he asks is, how many red edges can I have without having a red copy of Kn? And he found that this was the best possible construction. That if I want to have many red edges, but I don't want to have a red copy of Kn, then I need to split the vertices into n minus 1 parts and take all the edges between the parts to be red. But now, if you do this, you need each part to have size at most n minus 1, because otherwise you get your blue Kn there. And so then this is the best bound you could come up with this construction. So he could prove that for this kind of construction, that's the best you can do. Okay? But of course, there could be many other types of constructions. Right? So he tried to prove this quadratic bound. Unfortunately, he couldn't succeed. Okay? And the reason he couldn't succeed is because it's not true. Okay? So a decade later, Erdős proved that indeed these Ramsey numbers do grow exponentially. Okay? And so the upper bound was 4 to the n. The lower bound that Erdős gives here is square root 2 to the n. Okay? And kind of as remarkable as the result, because remember, Turan, who is a fantastic graph theorist, he thought it should be quadratic. Right? So this is way bigger than quadratic. Right? Turan was massively wrong. Okay? And what's remarkable about the proof, you need to find the coloring. Erdős doesn't find a clever coloring. Right? It's not some clever coloring that's hard to find. What Erdős says is just color the edges randomly. Okay? Don't try to be clever, just color them randomly. So for every edge, toss a coin. If it's head, color it red. If it's tails, color it blue. And then what Erdős showed is that if you do this, if you have this many vertices, then with positive probability, the coloring you get will not have a red k little n or a blue k little n. Okay? And in fact, what he shows by this argument is that almost all colorings on exponentially many vertices will be good. They won't have ordered sets. Okay? But, for a decade, people had been trying to find a single coloring, and they couldn't succeed. Okay? So this was a remarkable proof because this problem has nothing to do with probability. It's a completely deterministic problem, but the kind of only way we could solve it was to do this random coloring instead. Okay? And it's not a difficult proof, right? What's difficult is having this idea. Once you have the idea, it's a simple counting argument that you can write down in one page. Okay? So to wrap up, kind of where does this leave us in terms of the bounds we've seen? Well, we saw these two bounds. The lower bound is due to Erdős, the upper bound due to Erdős and Sekeres. And so we know the Ramsey number is exponential. What we don't know is the order of magnitude, or the rate of growth. Right? So the lower bound is square root 2 to the n. The upper bound is 4 to the n divided by square root n, perhaps. So these bounds, they're 90, 80 years old, respectively. In these decades, people have been working on this problem continuously. Right? So it's been kind of the major problem in graph theory and extremal combinatorics. So people have been working on it continuously. They've been looking at several extensions. So we've been able to make some improvements, but these improvements have been lower order, essentially. Okay, so with the lower bound, this is especially embarrassing. This is Erdős's lower bound. Okay, as I said, it's a simple one-page argument. The only thing we've been able to do in the 80 years since is to improve the value of this constant. Okay? And I believe I'm not wrong when I say we've improved it by a factor of 2. Okay? So now, instead of this c, we have 2 times c. Okay? Which isn't great returns of investment for 80 years of research, but this is a difficult problem. Okay? And the way you improve it is to, again, look at the random coloring, but to analyze it better. Okay? So to use more sophisticated probabilistic arguments rather than just some simple counting. Okay? So that's the lower bound. With the upper bound, we've had a bit more success. So what people have been able to do is to improve this. Instead of dividing by square root n, we've been able to divide by some super polynomial terms. So we've been able to divide by things like n to the log n instead, okay, which grows faster than square root n. It grows faster than any polynomial, but it's still insignificant compared to the 4 to the n. Okay? Until very, very recently, okay, so a couple months ago, there's a paper announced, a huge breakthrough by Campos, Griffith, Morris, and Saharas Bute. So what they proved is an exponential improvement. Okay? So that's this 4 to the n divided by an exponential amount. Okay? Massive breakthrough, right? Kind of came out of the blue. The paper is, I think, 56 odd pages. I haven't read it yet. And it's still on the archive. It hasn't. It'll take some time to appear in a journal, but people expect it to be correct. Okay, so it's the first exponential improvement in the Ramsey numbers since the original bounds. But again, it's conceptually a huge breakthrough because nobody had managed an exponential improvement. But there's still, a huge gap between the lower bound and the upper bound. Okay. So this is still going to be a very active area of research. So quite a few open problems. One, what is the correct base? Right. So before we knew that this constant c should be between square root 2 and 4. Now we know it's between square root 2 and 3.993. Right. So we've made some progress, but there's still a huge way to go. Okay. Another question is this is what I was talking to earlier. The lower bound, the Erdős coloring, is a random coloring. Okay? And from our subsequent research, we know that any good coloring has to look random in some sense. Okay? Whatever that means. But what we don't know is any way to color a graph without using randomness while avoiding these cliques. Okay? And forget about square root 2. We don't know it for any base. Okay? So even 1.0001 to the n, okay, we wouldn't know how to color that. Okay? So I talked about this coming from the Paley graph, okay, that you color things according to the quadratic residues. It's believed that you can do that for larger values of n as well. Okay, that if you want to avoid not k4 but some kn, you take some large Paley graphs, you take a finite field, you color the edges according to whether the differences are squares or not. We believe that that doesn't contain large cliques, but our number theory friends don't know how to prove that. Okay, so because they don't do their job, we don't get these colorings. Okay, these colorings, they don't give us exponential size colorings, but they'd be bigger than most of what we have. Okay, but yeah, this is again a major question to get rid of the randomness. And again, for applications, that could be quite important. But it's this very frustrating thing because the random proofs, they prove you that almost all graphs, almost all colorings will be good. They won't contain these cliques, right? So, but we cannot find a single one explicitly. And then there are many different extensions and generalizations of these, right? In different settings and things like that. So there are countless, many different problems you can study in Ramsey theory stemming from this kind of fundamental theorem in graph. So that's where I'll leave it for today. Just some kind of further reading. So as I said, this breakthrough from a couple months ago, massive breakthrough. So there's a Quanta article about it, which makes for an interesting read. So have you heard about Quanta before? It's this journal for popular science, right? So they write about scientific advancements in a way that's accessible to non-experts. Okay, so this has a very nice background about Ramsey theory, some discussion about applications, and then it talks a bit about this modern breakthrough as well, with quotes and interviews from experts in the field. Now, a bit of self-promotion, if I'd be allowed. Next year, there'll be the courses Graph Theory 1 and 2, so if you haven't taken those, Ramsey theory will be one of the topics in Graph Theory 2, so you've seen some of those things, but we'll also talk about other extremal problems in graph theory as well. Okay? So that's all. Thank you very much for your attention, and if you have any questions, I'd be very happy to answer them.
how can we encode this second story about the Bible thing in graph theory?
Yeah, so that's a good question. You can, yeah, so that was not a direct application of Ramsey theorem for graph, but more kind of this general principle that if you have a large enough data set, you'll find these ordered patterns inside them. And so even though this doesn't quite work in this graph theory setting, as I said, there are also applications to number theory. And then there are Ramsey theory questions there, which are quite similar, but instead of words, you're looking at numbers. And so there was a question of Erdős where he said, okay, if you take the natural numbers, okay, so one thing that is known and is relatively straightforward to prove, that if you take the natural numbers and you color them, red or blue, you can find arbitrarily long arithmetic progressions which are the same color, monochromatic. Okay? So what does an arithmetic progression mean? It means n plus d, n plus 2d, and n plus 3d, right? So these equidistant space things, just like with the Bible code. Okay? That's not too hard to prove. One thing that's important is that you can find arbitrarily long ones, right? So if you want something of length 100, I'll find it. If you want something of length 1000, I'll find it. You cannot find an infinite arithmetic progression, right? That it's quite easy to, again, provide colorings where you just take intervals and you make them longer and longer, and you swap colors between the intervals. What was a kind of major open question is the discrepancy problem, where, again, you want these arithmetic progressions, but now you fix them to start from 0. So you don't want to look at kind of n plus d, n plus 2d, but you want to look at kind of d, 2d, 3d, and so on. So kind of this version of the problem was called the Erdős discrepancy problem. Now here, instead of trying to make everything monochromatic, you wanted to make it biased more towards one color than the other, or something like that. And this was a major open problem. There's a polymath project about it. And then again, recently, a few years ago, I forget quite how many, Terence Tao proved the Erdős discrepancy problem. So he solved that. So yeah, it's not exactly in this graph theory formulation in that sense, but it's again this basic principle that you have this chaotic system where you kind of color things randomly, and then you want to find this ordered pattern. Okay, and so what does it mean in the Bible code? What is the coloring? Well, you can think of the kind of graph or the system as being the places, and then the colors are the letters. Right? So each letter represents a different color. And then we want to find not monochromatic things, but we want to find these nice color patterns which represent words that make sense. Okay, so it's a more complex formulation, but it falls under the same sort of philosophy. Okay.
You told about the Cayley graph. So the way we prove that R4 is larger than 17.
Yeah.
And I'm wondering if 43 is still a prime.
So R4 is bigger than 17. It's called the Paley graph. So not Cayley, but Paley. He was a number theorist. Mm-hmm. Yeah.
And I'm wondering if that works for 23.
Yeah. So it does not. The reason it doesn't is because this is still the lower bound, right, and not 44. But the real reason it doesn't, and I will get this wrong off the top of my head, but the way I defined it, or the way we define the Paley graph, right, x, y is an edge if x minus y is a square. Right, but remember with our graphs and our colorings, these need to be symmetric, right? So what that means is you need minus 1 to be a square. Okay, because suppose I say colored red if it's a square, right? So x minus y should be a square, but also y minus x should be a square because the edge is symmetric. So I need minus 1 to be a square. So I guess the reason it maybe doesn't work is, yeah, off the top of my head, I won't be able to tell you. I forget how the reciprocity works. But if your prime is such that minus 1 is not a square, then this coloring doesn't work there. Okay? And then the other thing is, it might just be that the numbers don't work out in this case, right? That even if it does make sense to make the coloring there, maybe that coloring in that instance has a monochromatic clique of order 5. Okay, so it's not a hard and fast rule, and even when the Paley coloring or the Paley graph does exist, the size of the largest monochromatic clique inside there, it depends on some other properties of n as well. So it's not that you will always get a good coloring, but kind of assuming some conjectures in number theory, I think you can prove a lower bound or an upper bound on how large the biggest clique will be, and that will still be a very good construction compared to what we know explicitly. Right? So yeah, there are some conjectures in number theory which would imply certain lower bounds, and I think the lower bounds are not exponential, but I think there's something of the order like constant to the n over log n, or n over log log n maybe, or something like that. So they're pretty close to exponential. But yeah, if you did need an explicit construction, a Paley graph would be a good place to start, and just to test if it works or not. Yeah, I don't actually off the top of my, I don't know what the best known construction is for 5, what the graph in 42 vertices is. But yeah, I think these bounds, they come from kind of heavy computational work. So people kind of search for colorings, and you have some heuristics. So, you know, what I said before about r to the 5, that there are these 2 to the 903 colorings, that's not quite true, right? Because there's a lot of symmetry, and you can rule out a lot of colorings very quickly. So there are people who do these kind of computer searches for colorings, and they have very good heuristics for kind of narrowing the search space, and therefore finding something more quickly. Any other questions?
May I ask
Yeah.
about the courses?
Yeah.
What would be the outline of the courses next year?
Yeah, so Graph Theory 1 is more of a kind of introductory course to kind of discrete maths. So it'll deal with kind of some more fundamental questions about graphs, so things about so graph connectivity. So one feature you want in a graph is that you can get from any one vertex to any other vertex. So what makes a graph connected, and spanning trees, and how many different ways are there of constructing these things. Another type of thing we look at is proper colorings of graphs. So this was about coloring the edges and avoiding certain things. But another important problem in graph theory is you want to color vertices. So you have a graph, you want to color the vertices such that whenever you have an edge, the vertices get different colors. Okay? And then you want to ask how many colors do you need? And you want to minimize the number of colors. This is another important and not very well understood question. And again, we'll look at some simple bounds. Okay, so it'll be more about kind of introducing graph theory, looking at some of the fundamental properties of graphs and what we can say about them. Then graph theory 2 will be more about extremal problems. Right, so Ramsey theory is an example of an extremal problem. Given little n, we wanted to know what is the smallest value of capital N for which this is true. Okay? Or Turan's problem was if we wanted to avoid Kn, what was the maximum number of edges we could have in the graph? Right? So this is what's meant by an extremal problem, that you want to look for the maximum or minimum value of a parameter under a certain constraint. And so we look at some kind of examples of extremal problems there. Ramsey theory or Ramsey's theorem will be one example. Turan's theorem will be another example. Okay, and also some examples in extremal set theory and so on. Again, we look at the techniques to solve them. Okay, and one of the techniques will be the probabilistic technique, where you do things randomly. Okay, but there will also be some other kind of algebraic methods and using polynomials. And so that graph theory 2 will be about the study of these extremal problems. Okay, so yeah, you can take these courses either as a bachelor student or as a master's student. If you haven't done any discrete maths or combinatorics before, then graph theory 1 would be required. If you've taken some sort of graph theory courses before, then you can let me know and we can see kind of what you've studied. And you know, if you've covered kind of comparable material to graph theory 1, then maybe you could just start with graph theory 2. Okay, so graph theory 1 will be in the fall semester, and then graph theory 2 would be in the spring semester after that. Yeah, so these courses were taught also not this year, but the year before. So the syllabus will be pretty similar.
声，谢谢戴尚年老师。
谢谢，Thank you。
旁边有点心，大家可以。